We are back. We are on the last video in chapter 3. So this is video 4 from chapter 3. And it's all about relative velocity. So velocity is measured relative to some reference frame, to some starting point. And it matters. You know this from riding in an automobile. If the car is parked in a parking lot and you're watching the traffic go by, it looks like the traffic's going pretty fast. If you start up the car and you join the traffic, your perception of the velocity is different because you are also moving. Normally, an observer thinks of themselves as being the reference frame. Another example of that is that if you're riding in a car and you look out the window, when you're accelerating, the trees look like they're moving really fast. You don't think of yourself as moving very fast. Once you get a constant velocity, it looks like the trees are moving and you have the sensation that you're sitting still, even though you know it's the opposite. The trees are stationary and you are moving. So your reference frame makes a difference. So we have an example. We're going to have a man run towards the front of a boat at a velocity of 10 meters per second. So if I'm going to have the man run towards the front of the boat, let's come down here and move his velocity vector. Whoops, I'm sorry. Move the man's velocity vector. The man is going to the front of the boat. This is the front of the boat. We've been to the island and now we're leaving. Okay, so he's moving to the front of the boat. The boat's velocity with respect to the shore is 100 meters per second. So we're going to have the boat, again, I think we'll have it, we're leaving, so our velocity is here. Maybe I'll make it kind of big. I'm sorry the arrows don't come out straight. You'll just have to forgive me. They're meant to be horizontal. I'm doing the best I can. So boat's velocity is 100 meters per second. Man's velocity is 10 meters per second. The way I have it drawn, we're in the same direction. So the guy over here standing around watching all of this is going to say, aha, you are moving away from me 110 meters per second. That's your velocity. When we write it, we would write it with subscripts. So the way these are read is the velocity of the man with respect to the shore. So it's always object and then reference frame. Man with respect to the shore is equal to the velocity of the man with respect to the boat plus the velocity of the boat with respect to the shore. So man with respect to the shore, man with respect to the boat, boat with respect to the shore. You should notice that on the right side where we're adding them up, the first subscript is the first subscript in the answer. The last subscript is the second subscript in the answer. And the ones in the middle are actually the same subscript and they sort of act to cancel each other out. So if we're running to the front of the boat and the boat's going away from the shore, we would say we're doing 110 miles per hour. I'm sorry, meters per second. Suppose we're going the other way. Suppose for some reason we are backing in. So now we're still running to the front of the boat, but I have the boat backing into the land. We've thrown it in reverse. I don't know, we're just crazy. So now we have the velocity of the man with respect to the boat, which is 10 meters per second to the left, plus the velocity of the boat with respect to the shore. Well, the boat with respect to the shore is 100 meters per second to the right. They point in opposite directions. We'd have to pick one of them to be positive. If you're the person on shore, you'd probably make the boat's direction positive and the man's negative, and you'd say, ah, this man is coming towards me at 100 minus 10 to make it 90 meters per second. So your perspective matters. All right, I'm going to put my little vectors back where I got them from, even though they are a little wackadoodle, and we will move on. All right. So if your vectors have two dimensions, x and y, then you have to care about x and y. The man in the boat and the shore only had an x direction. We are going to look at things with x and y directions. We're going to take an overhead view. We are hovering. We've got our drone out there photographing things, taking a movie, and we want to look at it. So in this case, we're going to break everything up into horizontal and vertical components, but we're not going to then bring them back together and find totals. And we're not going to work with a total vector and a total angle. So let's look at some of these examples. We have a boat traveling at 20 meters per second at 30 degrees east of north. So remember, start north, measure east 30 degrees. How long does it take the boat to cross a 30-meter wide river if we assume there's a 3 meter per second current moving to the east? And then the second question is, how far downstream does the boat land? So we have a little drawing. The boat is going, and you'll need to be provided with a picture. So here's my boat. This is the boat's velocity, this black arrow. It's 20 meters per second at an angle of 30 degrees east of north. So the dashed line is pointing north. North is always at the top of the page unless you're told otherwise. So start north, move east 30 degrees. So this 30 degrees is this little angle right down here where the dashed line and the arrow for the boat's velocity would intersect each other at the boat. It's way down here, not up here, and certainly not the right angle. The velocity of the current is 3 meters per second east, so it's this vector. And we know that across means this, so 30 meters is delta y. What do they want us to find? How long does it take? So that's a time. How far downstream? Well, if going across is delta y, downstream would be in the x direction. So we know the velocity of the current is 3 meters per second east. We know the velocity of the boat is 20 meters per second. Theta is 30 degrees east of north. We know that delta y is 30 meters. They didn't tell us there's an acceleration, so we will assume it's 0. We're going to let north and east be positive. We are looking for the time. You could write it as delta t or just t. Either one is fine. And we are looking for the total distance. So delta x. With relative velocity problems, and this applies to boats in a current, swimmers in a current, planes in the wind. For these kinds of problems where you have an object that travels at a rate and then an outside influence that's traveling at a different rate, we only have two formulas. We know that v total in the x direction is delta x over delta t, and we know that v total in the y direction is delta y over delta t. Why is this true? Because there is no acceleration. If there is no acceleration, your formulas just got really easy. You could use the same formulas we had before as long as you made acceleration equal to 0. And you'd end up, they'd reduce to the same thing. All right, so what do? We've got something at an angle. That means resolve into components. So we want to resolve things into components. I wanted to take a minute to write down, because sometimes they'll give you the current at an angle. The velocity of the current is 3 meters per second east. It's a horizontal vector. So velocity of the current in the x direction is 3 meters per second east. I'm not sure why that's there, to be quite honest. And the velocity of the current in the y direction is 0 meters per second. So this 3 meters per second east is only in the x direction, and there is no y part. Now we want to resolve the velocity of the boat into components. So to do that, we start out with a little sketch. The black arrow is the velocity of the boat. Remember, this little angle down here is our 30-degree angle. That means that the vectors that make the horizontal and vertical parts, the y1 points up and the x1 goes to the right. So velocity of the boat in the x direction is the red arrow. Velocity of the boat in the y direction is the blue. And the black arrow is just the velocity of the boat. So as always, when we notice that this word boat is a subscript, it's a subscript. So little v with a subscript boat to keep us straight. So we use sine and cosine. Sine is opposite over hypotenuse. So the sine of 30 degrees equals. So here is my angle. The opposite side is the velocity of the boat in the x direction. And the hypotenuse is the velocity of the boat, which they told us was 20 meters per second. To get the 20 meters per second out of the denominator, you multiply both sides by it. So it's 20 meters per second times the sine of 30 degrees equals the velocity of the boat in the x direction. When you do the math, the velocity of the boat in the x direction is 10 meters per second. I know it points east because of my diagram. Cosine. Cosine is adjacent over hypotenuse. So if we look at the 30-degree angle, the adjacent side is right here. It's the velocity of the boat in the y direction. That's the adjacent side. So cosine of 30 degrees is the velocity of the boat in the y direction divided by 20 meters per second. To get the 20 meters per second out of the denominator, multiply both sides by 20. So 20 meters per second times the cosine of 30 degrees is equal to the velocity of the boat in the y direction, which would be 17.3 meters per second. And it points north because that's the way our blue arrow points. So now what? We need the total velocity in the x direction and the total velocity in the y direction. So v total in the x direction, we're going to let east equal positive. That'll be the boat's x direction and the current's x added together. They both point east, so they're both positive numbers. So 10 meters per second plus 3 meters per second gives you 13 meters per second east. With the velocity of the total velocity in the y direction, v total y is velocity of the boat in the y direction plus the velocity of the current in the y direction. So what we have is v total y equals 17.3 meters per second for the boat and 0 for the y. So they add together and you get 17.3 meters per second north. Find the time to cross the river. We've only got two equations. V total y is equal to delta y over delta t. And why did I pick that one? Because we know V total y and we know delta y. If you had picked the x equation, we don't know delta x, so we couldn't have used it. So V total y is delta y divided by delta t. 17.3 meters per second equals 30 meters divided by delta t. Multiply both sides by delta t to clear the denominator. So delta t times 17.3 meters per second equals 30 meters. Divide both sides by 17.3, so delta t is 30 meters divided by 17.3 meters per second. That equals 1.73 seconds. We know the time to get across the river. The time to get across is the total time for the trip. So because you're going across and over at the same time, because you're traveling on the diagonal. So now we can say, we use our second equation, v total x is delta x over delta t. We know the total velocity in the x direction is 13 meters per second. We don't know delta x, but we'd like to. And we know the total time is that 1.73 seconds that we just calculated. To get the 1.73 out of the denominator, multiply both sides by 1.73. So 13 multiplied by 1.73 gives you delta x, and that means delta x is 22.49 meters. There are homework problems on the study guide. I think, as always, you need to see if you can redo the example probably before you do the study guide.